Welcome, everyone. My name's Jeff McGee. I am chair of the BCS Academy, and I'd like to thank you for coming along and to give you a warm welcome to this year's BCS Lovelace lecture. So the Lovelace Medal was established by the BCS in 1998. The medal is presented to individuals who have made a contribution which is of major significance to the advancement of information systems, or which has added significantly to our understanding of these systems. It's given in memory and honour of Ada Lovelace, mathematician and scientist, who of course you all know worked with and was inspiration to the computer pioneer Charles Babbage. Over the years, we have celebrated the contribution of many of our most influential and significant computing scientists, including Karen Spark, Tim Berners-Lee, Linus Torvalds, which are three that I've picked out for no particular reason. Tonight, joining this list of illustrious winners is 2015 Lovelace Medal winner, Professor Ross Anderson. So, Ross is distinguished for his many contributions to building security engineering into a discipline. Security engineering is about building systems to remain dependable in the face of malice, error, or mischance. It focuses on the tools, processes, and methods needed to design, implement, and test complete systems, and to adapt existing systems as their environment evolves. He was a pioneer in the peer-to-peer movement with his Eternity service, a forerunner of Freenet and Nutella. He was also one of the designers of prepayment electricity meter mechanisms used to electrify millions of homes worldwide, of HomePlug AV, which carries broadband over power lines, and is also used as a wireless LAN extender. In the world of finance, he documented the many ways in which payment systems can fail. He pioneered the study of API security, which led to the redesign of most of the hardware security modules used to protect bank PINs. He also made important early contributions to the tamper resistance of smart cards and the robustness of copyright marking systems. However, perhaps his most significant contribution and his highest impact has been in the economics of dependability and security. 15 years ago, he realized that information systems failed more often because of perverse incentives than because of poor design. If one firm was responsible for guarding a system while another bore the costs of failure, then trouble was likely to follow. This has led to contributions to policy debates on topics from the measurement of cybercrime through surveillance and privacy to the dependability of the internet and incentive compatibility mechanisms that are essential if we are to engineer security in the right place. Ross is a fellow of the Royal Society and of the Royal Academy of Engineering, and he wrote the standard textbook, Security Engineering, a guide to building dependable distributed systems. So I'm delighted that he is this year's winner of the Lovelace Medal. And to present that medal to him, I'm going to ask Philippa Gardner, who chairs the BCS Awards Committee, to present the medal. And I'm going to ask Ross to come up and receive the medal. Philippa, Ross.
So I have the real privilege of being chair of the awards committee. And 15 years ago, I was a postdoc in Cambridge doing another subject, but I wanted to find out a bit about what was going on in the department. So I sat in on some of the research seminars. And there was Roger Needham and Ross Anderson talking about security and in particular, what's it mean to break these various software systems. So it was enormously lovely for me to, 15 years later, to read what was going on with Ross's work and understand that that work I was hearing 15 years ago was, wow, having such an effect. And in particular, there were two Turing Award winners who wrote essays on why we should give Ross this award. So I'm delighted to present this award to Ross Anderson.
So before I ask Ross to present the Lovelace lecture, I'd like to ask Professor Martin Thomas of Gretchen College to give a short introductory talk. Martin, thank you.
Good evening. It's my privilege to provide just a very short bit of context for the importance of Ross's work. We live in an age of computers. It's an age that was conceived in the 1930s, born in 1948, and which, through the astonishing developments in hardware, has spread everywhere in the last 70 years. Computer hardware has become so cheap that it's all pervasive. And computer systems are very varied and complex, and that complexity is almost always put into the software in order that the hardware can remain general purpose and cheap. So the software is complex. And it's big. Typical app is already fairly big. Microsoft Office, you're up to several million lines of code. Modern car, you're up to 100 million lines of code. And whereas hardware designers, in order to achieve the very high reliability of commodity products in general, have to make sure they don't make any mistakes, and consequently invest an enormous amount of effort in validating the work that they're doing, software engineering has taken a different path. Software sold on the basis of functionality. Software purchasers aren't able to really tell the quality of the software that they're buying, whether it's safe, whether it's secure, at the point that they're buying it. And under those circumstances, much less effort is put in by software people into the analysis and verification that is commonplace in the hardware world. And the consequence of that is that software contains an awful lot of errors. This is an experiment that was carried out by Watts Humphreys a number of years ago, showing that even the top 1% of software developers makes 11 errors per 1,000 lines of code. These are the kind of defect rates that turned up when an analysis was done of the software in part of the C-130J, the Hercules military aircraft. And as you can see, in the worst cases, some of the C modules, you were getting an error every 2 lines of code. Even in the best case, you were getting an error in every 250 lines of code. These are serious issues. And what happens when there are lots of errors in code is that projects overrun. And when projects overrun, one of the things that then happens is that the project slips further because people start cutting corners. In particular, they cut out the testing. This is a memorandum, very recent memorandum, December memorandum from the Pentagon about the software in the F-35 fighter that we're buying to put on the aircraft carriers in the UK, and which is also the main new fighter for America, which has got a lot of faults in the software. There have been a lot of press reports about it. And as the memo shows, they're now considering cutting down the testing in order to try to meet the deadlines. So the result is that the software we've got has got an awful lot of errors in it. And that leads to an awful lot of difficulties. So the consequence is that the software infrastructure on which we depend simply can't carry the weight that we place on it. And there are many examples of this that we see in the newspapers, day after day after day. Here's a medical example. It's not just the cars that get it wrong. And these things also have major impacts in terms of privacy and in terms of security. Websites get hacked, personal information is stolen, and that causes huge damage in all sorts of different ways. The Ashley Madison website was hacked. You may have read about it. And it's led to marriage breakdowns. That hack has led to marriage breakdowns and to suicides already. There's a lot of attacks on healthcare data because it's very valuable. You can sell somebody's medical record for several times, orders of magnitude more than you can sell their credit card data for on the internet. Of course, financial attacks also. Plenty of these sorts of attacks going on. Now, companies ought to worry about that, and increasingly they do, but it's not leading to people taking the steps to ensure that the software is robust enough to be able to withstand those attacks, that there aren't the vulnerabilities there. Most companies reassure themselves by saying that nobody has both the capability and the intent to do real damage, particularly to the critical national infrastructure. But that's changing. Very recently, the Chancellor in Cheltenham said that he had intelligence that ISIS were attempting to get the capability and already had the desire to attack the critical national infrastructure. He said anything that's online must be considered a target. The National Security Council, in doing this year's National Risk Assessment, has identified 4 Tier 1 risks, and amongst those is a hostile attack on cyberspace, considered as important as pandemic flu, as international war, or as a major natural disaster. So this is the context in which Ross's work is operating. The sort of things that have to be done are, they require a deep understanding of the security environment, of computer science, of the politics, of the economics of software development. And of course, just at the moment, the politics is live because we have the drafting investigatory powers bill in front of Parliament, 300 pages of draft bill. There are very few citizens who are going to be able to understand the details of that, very few parliamentarians who will understand it during the debates and the voting. It needs experts like Ross to be able to illuminate the politics, the democracy, the privacy, the economic structures that are actually influencing these things. So that's the context that makes Ross's work so important. He shines a light on this world in ways that enable us as citizens, as people who have any kind of influence, to understand more about the forces that are operating and to exercise more control to help us to design the future that we and our children will live in. That's the context for Ross's work. That's the world that he illuminates, and I'm really very, very happy he's on our side. Thank you very much.